to the third part of electrolysis. I'll be going over the electrolysis questions that you can receive in exams, and by using, you have to watch the previous video just to get an overview on how electrolysis works. So let's take a look. We're going to first we will have the electrolysis of an aqueous solution of copper to chloride. Then we have the electroplating of an iron spoon with silver, electrorefining of metals, purifying them to a high percentage, recycling of aluminium, and the production of chlorine gas in the chlor-alkali industry. So let's start with number one. We have copper chloride. So let's draw our little electrolysis of copper chloride quickly. So we have a container. We have two electrodes, carbon electrodes. There is then, let's push this down. All right, and there's wire. Then we have a power source. Let's put the positive side on the left, and then it looks like that. We have some, we have solution of our copper chloride in here. So we have Cu2 plus ions and chlorine ions, and obviously we have water in here. So just using our logic, we have the battery, so then the electrons will be on this side, will go in that direction, so that'll be our negative side. And therefore positive side, remember reduction takes place at the cathode, so let's try and determine which one's going to be the cathode. Let's take this copper 2 ions are going to be attracted to the negative electrodes, so we have copper 2 plus is going to take 2 electrons from there, forming copper as a solid. So we have 2 plus going to 0, which is then reduction. Reduction is at red cat cathode. So this is the cathode. This is how your thinking process must work. And then the chloride ions will then go to the positive anode, or we'll say why it's anode now. So we have Cl minus will donate an electron. Will form Cl2 donating an electron, but you actually have to balance this out. So here we go, it will look like that. And this is our, so this is reduction, red cat, and this is our oxidation at the oxan, at the anode. So we know then this is the anode. And it will differ from galvanic, but anyway, so the chloride ions are anions, because anions always go to the anode. All right, that's the important thing. All right, so, but there is a catch, as we saw in the previous video. We have to determine whether the copper ions will compete with water and whether the chloride ions, or they will compete with water, but which one will undergo reduction in terms of the copper 2 ions or water, and which one will undergo oxidation in terms of the chloride ions and water. But we know that it will just work out like this, but let's just prove it. So we write down the two reductions. So we have copper 2 plus going to copper 0, and we get the this exact reduction of water from the standard reduction potential table. And we write down the E naught values. So let's take a look. So if we take a look at these two values over here between copper 2 plus and water, we see, let's take a look at which one will be reduced. We said in our rules earlier, we have to look at this, the one of the higher reduction potential gets reduced at the cathode. So which one has the higher value? If you look at our number line, that will be this one. So this one will not get reduced, but that one will. All right, if we take a look at the oxidation reactions. All right, so we write down the oxidation ones, but now there's two water reactions that are in that table. So which one do we use? Now, remember that water is being reduced over here, or the hydrogen in it, but on this side, we have electrons on the right-hand side, meaning there's a loss of electrons, so it's oxidation. So we don't want to use this one, because it's the reduction equation there, so we're going to have to use that one. So we take it the E naught values, and if we compare those two, we know that for oxidation, the higher, the lower E naught value should be oxidized, which is actually water. But in reality, or in real life, this will be oxidized. The reason is that your concentration of chloride ions will be much greater, so therefore will be more easily oxidized than water itself. So that's important to know. All right, so I just wrote that down again. This equation has a lower Enough value, so it should be oxidized, but the concentration of chlorine ions is very high, therefore it will be favored like in real life. So let's write the half reactions down and see what happens. We don't have to write them down because they're over here. So I'm just going to rub this out, and then I'm going to rub these things out over here. So we're going to take a nice look. So what happens is oh, by the way, this is green. It's a green solution. That's kind of important. But as this reaction takes place, copper will form on what? The anode or cathode? It forms on the red cathode. It will form on here. So you'll have like a brown precipitate of copper metal forming on that cathode. Excuse me. And then so it'll be like a reddish brown color, reddish brown. And also the sort of the green will sort of the green color of the solution sort of dissipate into a more colorless form. Okay, and if you look at the chlorine, it will form it's like a yellow green gas. Interestingly, they probably use this type of or one of these electrolysis reactions to form chlorine gas, capture it, and in World War I they actually used it as a weapon, released it when the wind was blowing towards the Germans or towards the other side. They released tons of chlorine gas, blinding temporarily, maybe even permanently, the soldiers so that they couldn't fight, taking them out of the battle. So chlorine gas was used as I don't know if it was a biological weapon, but it was a weapon of war, and it's kind of illegal now to use it. But all's fair in war, right? Depending on how desperate people are. So anyway, let's carry on. We have to write the net equation down. So if you take a look here, I'm going to write the net cell equation. We have two electrons, so we just plug it down. We have Cu2 plus 2Cl minus, the arrow CuO plus Cl2 as a gas. We just put in our little subscript here. Dissolving water. Good. Easy peasy. And you can also maybe combine these two if you want. It doesn't really, it's optional, you don't have to. Right, then we can increase the rate of this reaction by doing a few things. So in electrolysis, you want to increase your voltage by adding more cells or batteries, like increase the number of cells, or and you can also increase or lower the resistance in the solution. So let's just make a few points here and then we can see. All right, so we can increase the voltage by adding more batteries, which will increase the energy for the redox reactions, for reduction and oxidation. And also if you increase the voltage, you'll also increase then the current, right? So then, what? Psychedelic what? Yeah, I don't know what that was. Something about aliens landing or something. Anyway, so that was a weird pop-up. I haven't seen that before. Or you can reduce the resistance by increasing the concentration of the electrolyte. Move the electrodes closer to the carbon electrodes. You can increase the size or the total surface area of the electrodes. And also, if you fully submerge the electrodes so that they have a higher contact area with the solution, that will also decrease the resistance. Okay. Yeah, so high electrical conduction. A high electrical conduction, or let's just say electrical conduction is inversely proportional to the resistance. Alright, so you have a high electrical conduction if you have a low resistance. They're inversely proportional. Okay, so the next reaction we're going to look at is we take an iron spoon and you coat it with silver. So you go to the shop, you buy a silver spoon, but you then see, oh, made in China, and after you wash it a few times, you get a nice, cheap undercoat of some type of inexpensive metal covered with expensive, thin layer of an expensive metal like silver or gold. So kind of have to watch that. Depending, they can sort of trick you at the shop sometimes. Oh, look, silver spoons, because technically it is silver, but then, I mean, like silver covered, but the whole thing is silver through and through. So anyway, so this is how you do it. Let's take a look. So you can electroplate a metal with another metal through electrolysis to give it various properties. Maybe it just looks more pretty. The aesthetics will increase, or you can coat maybe something like iron that rusts easily with maybe chrome for the use for in vehicles. And yeah, you can also for various other reasons. Now, the metal that is to be covered will be at the negative electrode, and at the positive electrode you'll actually have like the metal you want to cover the other metal with attached by the positive electrode. And I'll draw quickly. I'll draw a picture quickly. So we have a container. We have our two. Actually, we have a battery. So let's make it. Let's just go standard. Negative side here, and we have positive side over here. So it'll be negative side and then positive side. And on the positive side, you'll have the actual pure metal you want to cover the other metal with. And in solution, let's just make it, in solution, we'll have whatever this is bonded to something that can dissolve in water. So AgNO3, because everything that's bonded to NO3 will dissolve. That's in the water. Okay, so we have this setup here. We have the iron fork on the right. Look at that beautiful fork. Almost looks like what Dan's top he wears sometimes. Anyway, and then we have that pure Ag metal, and then in solution we have whatever this is in a compound form, something that makes it able to be dissolved in water, which is NO3. We'll always do that. So it will be in aqueous form. So the solution will be a silver nitrate solution in this case. Okay, there's also a bit of a KCN, potassium cyanide in here. It's just so that the silver concentration is constant, but we're not really going to mention it. We just know about it. Okay, so what happens at the anode? What is the anode? Let's quickly take a look. So we have the negative side over here, and we have an iron fork, Fe fork. And on the left hand side we have the positive side with our pure metal. So let's start on the positive side, because I'm going to show you what happens. So what happens is the Ag metal will constantly throw in silver ions into solution, constantly. So this, as this reaction carries on, and the silver ions plate this iron fork, so the ions in solution will constantly go there, so it will be replenished by this metal by the positive electrode, or as the positive electrode. So the piece of silver metal will constantly lose mass, producing these Ag plus ions to supplement the ions that are being used up plating the iron fork. So what's happening? Ag is by the positive side. Ag is being converted to silver ions plus electrons. So what is this? Is this reduction or oxidation? We're going from a 0 to +1, so it will be a oxidation. And oxidation takes place at anode. So this is then anode. So you use that logic, you always figure out which one's which. And then the other ones obviously then the cathode. And these silver ions will be attracted to the cathode, the negative side, and forming a solid. So let's write that down quickly. Precipitates out, and this will cover the surface of the iron fork, increasing the mass of the fork, right? Because you're adding more, silver atoms to it. So the cathode increases in mass, and the anode will decrease in mass with the silver metal over there. So they probably like to ask you, they will like to ask you in multiple choice or in the questions themselves. So, right, so very important. Now let us say these silver ions form silver as a solid, right? We can use our normal stoichiometry to actually figure out like what mass of silver ions actually were, how much moles of silver ions was converted to moles of silver metal, which we then can convert to mass, right? So we use the ratio in a balanced redox or half reaction and we can actually figure this out. So let's just say they say we have 0.5 moles, like over this various amount of time, was used up or transferred to the other or in the electrolytic cell. So how much moles of Ag plus was converted in? It will also be 0.5 because it's 1:1. So the 0.5 moles of Ag plus will take up 0.5 moles of electrons. Therefore, the amount of silver added to the spoon will be then, yeah, so maybe it's better to just write it like maybe just the whole thing out. So if 0.5 moles of electrons are used up, then we form 0.5 moles of silver metal. So what is the mass of silver added? It will be mass equals to moles times molar mass, like straight up grade 10 work here. And the molar mass of silver is 108 grams per mole, and we end up with half of that, which is then 54 grams. Very, very, very important. They love these type of questions. So what they can actually do is like give you the amount of particles of electrons, like the amount of electrons, and then you actually have to work out via amount of particles. So it's amount of electrons to amount of ions to, you know, so it can be quite a nice type of thing. But we use our mole map. We write the whole equation out and we can like plan out what we're going to do. But I think there is a past paper I'll do on this just now. But very important to understand this. Right, during this reaction, the concentration of the electrolyte remains the same because it's constantly being replenished by the silver metal over there, losing its mass over time. And obviously the rate of oxidation is equal to the rate of reduction, which is quite important. And just for interest's sake, what if we wanted to coat this iron fork with copper? What changes will we make to this whole setup? Well, first of all, we want a plate with copper, so we can put copper over here. And then in solution, you want copper bonded to something else. So we can have something like copper nitrate, or we can have something like maybe copper sulfate, but just choose nitrate because it will always dissolve, right? Everything it's attached to will make it aqueous. It won't be something that precipitates out, or it will dissolve. All right, so that's how that works. Now, taking a look, so you saw the logic of how to figure out what is anode, cathode using our oxan and the red cat. And then this very important thing, but I will do a past paper question on it where they actually, it's like a level 4 question, so we can take a nice close look at that. So stay tuned till the end of the video. Let's go to the next one. So the electrorefining is purifying of metals, is where we purify metals using electrolysis, right? And it's by taking like an impure sample of the metal and at the anode, and then putting a pure sample by the cathode, so that the actual, let's just say for instance copper, pure copper will be attached, be removed from the anode, and it gets attached to the cathode, and the impurities fall to the floor. So let's take a look. Let's draw a quick picture. So we have our container, we have our battery. Let's draw it this way. And then we have our two metal samples. This is the pure one, maybe. Well, let's take a look which one's the pure one now. We have copper and copper. Let's say if we're getting the test. And then we just put it like this, attach it like that. And then in solution, it will have to be a copper something that can dissolve in water. So let's just make it copper sulfate, and that'll be aqueous. So what happens is now, we can take a look at this negative side. So that's negative side and positive side, and now we can determine what gets reduced and oxidized. So what happens is we have copper 2+ ions in solution, and either they'll go this way to be reduced, forming a solid, or they'll go the other way. But which way is it? So the copper ions in solution will want to gain electrons, so they will go to that side, and this is reduction from 2 plus to 0, so it's reduction, red cat, so they go to the cathode. Negative is the cathode. And like we said earlier, you get the pure sample, and then you actually suck up all the copper ions to the pure sample. So your negative cathode will be your pure metal, which in this case will be copper. And on the right, we have our impure. So what happens is the impure, by the positive side, the copper will form these copper 2 plus ions, which will then form copper as a solid on the cathode. Quite interesting, eh? So what happens is that the positive anode will lose mass, and the negative cathode will gain mass. So you will increase the amount of mass here, and you decrease the mass here, and impurities fall on the floor, the sludge or whatever. So looking at that's red cat, reduction at the cathode, and we look at oxidation at the anode. We have copper forming copper 2 plus ions plus 2 electrons. Right, and a copper sulfate solution is blue, as we know from prior experience. You know, what's that guy who took a nice block of copper sulfate and chucked it in his mouth, you know, because it's a sweetie. So hope he's okay. But anyway, so copper sulfate is blue. You should not forget that because of our experiences. We have experience together in class, thanks to two choppers eating chemicals in my classroom, thinking, telling one line to the other one, telling them it's a sweetie. You kill each other. Bunch of crazy kids, eh? Choppers. I've never in my life seen someone chow a chemical out of a container. It's nuts. Anyway, lesson learned, I guess. So, moral of the story: don't eat chemicals. It's nuts. You can actually just die. So this guy like invites death into his life constantly. You know, swimming when you can't swim. Okay, I'm being insensitive. Let's carry on. Hey, we all have weaknesses, eh? So yeah, good memories. So now, anyway, or memories nonetheless. So we have this copper sulfate solution, so it is nice blue color, and the rate at which these impure copper sample is producing copper ions is the same as the rate at which it will be reduced to that pure copper side by the cathode. Okay, and the impurities, such as like things that are less reactive than copper, in this redox table we have, they will form like a sludge over here. I shouldn't actually draw that there, but they'll form like a little, what am I doing, at the anode. They'll form a sludge down, oops, deleting the whole thing, form a sludge down here. But metals that are more reactive than copper will form, will actually just go into solution. Until maybe the concentration becomes a bit too high, and then they might actually be reduced up here if the concentration is too high, the impurities. Things that are more reactive than copper. All right, so that's how that one works. Straight up, easy peasy, eh? And just remember, they can ask something similar to this type of stoichiometry question. We'll get to that later. Okay, let's look at the fourth one. Okay, so the recycling of aluminium. Aluminium ore is bauxite, and bauxite contains like iron oxides and all kinds of other things, but they purify it. Anyway, but like it's found in this place called Australia. Now, it doesn't really exist, but many people believe that Australia is a real place. But anyway, bauxite comes from Australia, and it is a real place. And because where do we get that from then? Unless it comes from somewhere else. Maybe someone should go visit and let us know if Australia is really a real place. But so, we get this bauxite from Australia, we ship it to Richards Bay, there's a factory there, we melt it down, the Al2O3, and then, because then if we melt it, this ionic compound, we get aluminium ions and oxygen ions. So when the process of the electrolysis of aluminium has a few steps. The first step is we take this bauxite ore, which is washed, ground, and then dissolved in sodium hydroxide, and then so we can get pure AlO3 out of it. So remember, bauxite is like it's got a whole bunch of different. It's got iron oxide, all kinds of other things. So they wash it with NaOH, sodium hydroxide, and they get this AlO3 compound, which is also called alumina. Yeah, the waste products is usually like iron oxide, and they pump it into dams. Step 2, the AlO3 is dissolved in molten cryolite, which is Na2AlF6. Check this out. So it is dissolved in this compound that is in a liquid form. The reason being is because alumina has got a very high melting temperature of like 2000 degrees Celsius, and that requires a lot of energy, electricity, which we don't have in our country, and it's very expensive. So what they do is they dissolve this alumina, Al2O3, they dissolve it in this substance over here that's melted. So instead of trying to melt this at 2000 degrees Celsius, we dissolve it in here, and then we only have to melt the, this can be melted to, or put in liquid form at 1000 degrees Celsius. So you save some money and ESCOM the trouble of trying to keep up. All right, so this is the setup that is used. You have 3 graphite or carbon, graphite, carbon and form of graphite. You have 3 graphite electrodes over here, and you have a lining also on the surface of the container, the steel container, which will also be made of graphite. So you will connect the electrodes to the positive side of like a power station, not a battery, because you need quite a lot of energy for this, and the negative side will be the actual lining. So what happens is that at the negative let's call it the lining, we have oxygen ions being bubbling out as O2. So at the negative we have an increase in the oxidation state. So if there's an increase, it will be a oxidation. So this is oxidation, and therefore this is the anode. And excuse me, it will give off electrons, so it will have to be reacting over here by the positive, let's just say, the positive, will it be anodes or cathodes? Reduction? Was this oxidation happening here? Oxidation is at the anode. So these will be anodes. Oxidation at the anode. And what happens at the cathode, which will be the other thing, our negative cathode. Now in electrolysis or these electrolytic reactions, the negative side is always the cathode, but it can be confusing if you work with the galvanic cells as well. So what happens here is that aluminium gains electrons from the negative cathode, obviously, and forms a solid. Easy peasy. And then we just add these 3 together. Now we have 3 electrons, 4 electrons, so we need LCM them to, how much is that? 12, right? So we need 4, like that, and then we go 6, 3, and 12. Cancel out the electrons, and then we get our net reaction of 6O2 minus plus 4Al3 plus. So we end up with oxygen and aluminium as our products. Okay. They could also say, or we can say it's just Al2O3 in a liquid form. But it's okay, just leave it like that. Now there's another thing that happens, or what happens is the aluminium will sink to the bottom, forming a aluminium at the bottom of the container as a liquid, and then they just tap it out so that you have your pure aluminium coming out the side there. Interestingly, they actually the electricity going through the system, the voltage is quite low, like 5 volts, but your current is like 100,000 amps. So it really heats up this system because of the high current. Remember, we studied that in grade 11, I think, where electricity is transported over long distances at a high voltage, low current to reduce the amount of energy lost as heat. But at high current, low voltage, you actually lose lot of electrical energy as heat at a high current. So interesting. Now, what also happens is the carbon from the electrodes, the cathode and anode, actually react with the oxygen, forming carbon dioxide. It's at very high temperature, so it's going to be quite an easy reaction to happen there. So the anode is constantly being burnt away and must be replaced when it kind of gets quite thin. All right. They do speak about environmental effects, but I mean, yeah, produces carbon dioxide, and carbon dioxide is bad. Global warming and all that. So, the what's the sludge that's from the washing of that bauxite can also cause environmental damage when they dump it and poison groundwater or whatever. And when you actually make a mine or a chemical plant like this, you need land, and using land is bad for the environment. And then some other problems could also be economic problems, where aluminium extraction requires a lot of current, a lot of electricity, and it's therefore expensive, and it's rather cheaper to recycle it from than to produce it. So like that's why recycling of aluminium is quite nice. So yeah, there we go. So I think that was the last one. We have all those done. Oh, the one is one more. So let's do number 5, which is the production of chlorine. All right, so let's take a look at this membrane cell we've got going here. So in the middle, we have a membrane. It allows only sodium ions through, but not chloride and hydroxide ions. That's very important. So what happens is that water is pumped into there, and sodium chloride solution that's concentrated, let's just say a high concentration of sodium chloride solution, is being pumped into there. And what happens is we have a power source, and the positive side will be made up of a certain metal, and the negative side of another metal. So they use titanium for this side, and the other side they use stainless steel or nickel. Let's just go nickel in for the cathode. They are inactive or unreactive, and they can be used over and over and over. So the titanium and the nickel electrodes can be reused. So this membrane is a permeable membrane, a selective ion permeable membrane, which only allows certain ions through. It's made of fluorocarbon polymer, and that's how that works. So in this solution, we've got water, we've got sodium ions and chloride ions. So what happens? The chlorine ions will be reduced by the they will be oxidized almost all. Anyway, let's just write it down. It's easier if you just do it this way. They'll form chlorine gas. There'll be 2 of those. So they will be chlorine will be oxidized and increase in the oxidative state. So chlorine is oxidized. Oxidized means it's oxidized at the anode. So this is the anode. And at the negative electrode, we have sodium. You'll think sodium will form sodium metal, right? But actually what happens is that the water gets reduced. So, okay, so you actually are forming at the anode, where oxidation takes place, you're forming chlorine gas, which is collected. And at the reduction of the cathode, we're forming hydrogen gas. And you have this hydroxide, which will then actually bond with the sodium ions to form NaOH, which is also then collected. So let's take a nice closer look at what else happens. So when this concentrated sodium chloride solution goes in, the chlorine ions get used up and sodium ions gravitate towards the right in this case, and we also tap out the diluted now sodium chloride solution, and you constantly replace it with fresh amounts of sodium brine, which is the sodium chloride solution. And on the right side, by the cathode, we also tap out the NaOH solution. Okay. So back to this membrane. The reason we want the sodium ions to cross over is that it keeps the two half cells like electrically neutral, and that there's no mixing of products. That's why those two don't get let through, the chloride ions and OH minus ions. You don't want them to go through. If you allow the NaOH ions through, it will allow a electrical neutrality to take place, which is great. So at the cathode where reduction takes place, either you have the sodium ions being reduced or water being reduced. Now, water is a stronger oxidizing agent than Na+, and therefore it will definitely be favored in this reaction, so that will not take place. You can also take a look at your E0 values from your table as well. So we form hydrogen gas and these hydroxide ions, which will then bond with our sodium ions, forming a NaOH, which is then tapped out as we saw in this picture over here. Now at our anode, where oxidation takes place, so if you take a look at the anode, we have two choices. Either our water is going to be oxidized, or our chlorine. Remember, I spoke about these two separate equations. The one is the reduction of water, and the other one is the oxidation of water. Anyway, so either one of these two get oxidized, but which is it? We use our rules, as we stated earlier, looking at which has the lower reduction potential, or we can just take, we just see that you see it's similar to our first example where the chloride ions are in a much higher concentration, so that's why this will not happen, because of the concentration difference. Alright, so these will form, at the anode you have chloride ions forming chlorine gas, and at the cathode you have water forming hydrogen gas, hydroxide ions, which then bond with sodium ions in solution, forming our sodium hydroxide. So let's just write down the next reaction and see what happens. So if we add these two half reactions together, we get this, but we can also sort of complete it by adding that NaCl, the sodium ions. And then we'll have a 2NaCl and a 2NaOH over here. And that'll be in aqueous form, obviously. Alright, so that's lovely. Now, some uses of hydrogen is to produce hydrochloric acid, to produce ammonia, rocket fuel, all kinds of other things, nylon, making of nylon. Chlorine gas is used in warfare to kill people. Okay, we don't use that as a reason. But for water purification, make PVC piping, to produce hydrochloric acid as well. And sodium hydroxide is used to make soap, bleach, to extract aluminium, to make paper, and wastewater treatment as well. So we just need to know like two of each, just in case they do ask that. And there's some environmental risks again. Hydrogen is explosive, flammable, explosive. Chlorine gas is highly toxic. If you use it on people like they did in the First World War, breathing problems, you can damage your lungs. because the chlorine gas forms hydrochloric acid in your lungs. You're actually acidifying the mucous membranes or whatever, causing great damage. And it's chlorine is used in the manufacture of drugs and narcotics, which can be very dangerous. And then also chlorine can be used as a nerve gas. Sodium hydroxide is also highly flammable and toxic. That should be some of the environmental or health risks that can happen. So let's take a look at the past paper question and see if we can do it. All right, so here's our paper from 2022. Let's take a little read at the first piece there. The diagram below. Now this question 9 will be an electrolysis question or electrolytic cell question, and question 8 will be galvanic. So let's take a look at question 9. It's 13 marks, 10% of your paper. Not that bad, eh? So let's take a look. There's a simplified cell used for the electrolysis of concentrated chromium chloride. So you have Cr3 plus and Cl minus ions. Electrodes R and T are made of carbon, so, and you have a battery over here. So the net cell reaction is, they give it to you. And define the term electrolysis. We should know that electrolysis is the chemical process in which electrical energy is converted to chemical energy. So yeah, that's 2 marks, easy peasy. And there's some other options there, but we use our examination guidelines, right? In 9.2.1, the question is the graph below, not drawn to scale, represents the changes in mass of electrode T. There it is there. During electrolysis, right? So what's happening to the mass of it? Is it increasing or is it decreasing? There's an increase in mass. Some tips there. Looking at this equation, I wonder which product is forming at that electrode over there. So write down the half reaction that takes place at T. Because the mass is increasing there, that should be forming, isn't it? So let's write it down. Maybe not, yeah. So we have chromium plus 3. How do I know this? Because of that compound. Oh, yeah, they told us the compound. So you have CrCl3, it's grade 10 work. The whole compound 0. We know chlorine's a -1, so Cr has to be a +3 to make that a 0. +3 to make that equal to 0. Okay, that's how I know. Alright, so chromium 3 plus will receive 3 electrons to form a chromium solid because its mass is increasing on that electrode. So what's happening here? We're going from a +3 to a 0. That is a reduction, and that happens at the cathode, right? So know immediately this is our cathode. And because it's taking up electrons, this will be negative. All right. And then, yeah, I mean, that's quite a straightforward. Okay, now they ask a really nice question over here. A current of 2.5 amps is passed through the cell for 10 hours. So we have current and we have time. And time is equal to 10 hours, which is how many seconds? Anyway, let's just say it's 10 hours in seconds will be 10 hours times by 60 times 60, right? 60 minutes times 60 seconds. We'll just plug that in, it's fine. And so they want to know the total charge, which is Q, that flows through the cell. We have a Q, we have an I, we have a T. Sounds like grade 9 work. So let's see. Q equals IT. Or I delta T. In the formula sheet, it should be a small q here. And then I, current is 2.5, and your total time then is that 10 times 60, 600, is that 36? Anyway, I don't feel like working it out. And we get an answer of, now I feel like working it out, hold on. We get 90,000 coulombs. I mean, isn't that an easy 3 marks? I like this question because they're bringing in other things from other sections. And then they want to know, what is the value of x at the graph? 6 marks. Beautiful question. So what do? We take a look at this over here, our reduction of chromium 3 plus. So let's paste it down here. Remember earlier I said we have to watch out for this type of question where you get like electrons, you have to work out the moles of something else or the mass of something else. So we can see that we have 90,000 coulombs over here. But we also have this formula where the number of electrons is equal to the charge divided by the charge of one electron, right? So we have 90,000 coulombs divided by the charge of one electron, which is 1,6 times 10 to the negative 19, and we get 5,63 times 10 to the 23 electrons were transferred. That is the number of, that is the N, the number of particles. So we can actually put it in a ratio like this. In a ratio like this from the equation, and chromium is 1:3 in terms of electrons. How many electrons do we have? We have 5,63 times 10 to the 23 as 2, and we use our calculator and we get, remember going up divide times down, so divide by 3 times 1 down, and then we get 1,88 times 10 to the 23 particles of chromium, which is chromium 3 plus. So that is the, oh sorry man, what I'm trying to do is this, I'm trying to do those two. I don't know why I did the 3 plus, sorry about that, let's take that out. So we have this amount of particles, that is the N of Cr as a solid, right, is equal to 1,88 times 10 to the 23. So now from our mole map that you guys should know, I think we did it in this direction, N over Na, we can get this directly to that, right, by skipping out the mole calculation over here. So let's put it in. So in terms of chromium, we have 1,88 times 10 to the 23 over the Na value of 6,02 times 10 to the 23 equals, so a small ma, mass over the molar mass of chromium, which is 52, and we plug that in our calculator and we get a mass of 16,12 grams. So excuse me, but just hold on now. If you take a look at this graph, we are adding 16,12 grams, right? From the starting position of 2.2. So the actual mass of the whole cathode, which starts off as 2.2 grams, will then have a mass of 16.12 plus that 2.2 grams, right? So therefore the mass of the cathode is equal to 16,12 that we added, plus our original 2.2 grams of the cathode itself, and we get 18,32 grams. Not that bad, eh? It's quite a lovely question actually. That's definitely level 4 question. But the key is the value of X, the value of X is the mass of the electrode or of the cathode. That's actually what they're asking. And it starts as 2.2. How much mass did we add to it? Using our value from 9.2.2, the total charge that flows. Total charge that flows means we know how many electrons were transferred, and therefore we know how many particles of electrons, right? Which is then put in a ratio with a chromium solid as 1:3 or 3:1, doesn't matter. And we can find, knowing the amount of particles of electrons, we can find the amount of particles of chromium or atoms of chromium. And then from there we know the particles. We can go straight off to our grade 10 stoichiometry, getting the mass added to the cathode, and so we just add it all together and get 13,32. There we go. So that's this section done. And I hope you guys understood sort of what was going on here. Right, have a good exam. Take care.